completed the theory identification of atomic mass.
Right. So, getting into the details of redox reactions, first thing we need to basically understand here are concentration terms. Okay. So, let me first introduce you what are concentration terms. Concentration terms include molarity, okay, molality, mole fraction, normality, and percentage compositions. Correct. To learn more in detail about concentration terms, we need to understand what is solution. Solution, in short, is mixture of components, okay, preferably in same phase, which means if one is in liquid state, the other must be also in liquid state, like that. Okay. So there are two terms that we will be using: solute, which usually is in lesser quantity, and then we have solvent, which is in larger quantity. Okay, this will retain the phase in solution. The one which retains the phase in the solution, that is what we call it as solvent. So together we use the term solution, which is basically solute plus solvent. Okay. Now putting the definitions together, molarity, capital M, is always defined as number of moles of solute upon volume of solution in liters. Okay, so this is how we use it as a formula, N by V. Okay, units being mole per liter inverse, or simply capital M. Got it? Another definition is molality, which we define with small m, which is about number of moles of solute upon weight of solvent in kgs. This we write it with small m, which is N by weight in kgs. Okay, and this W is of weight of solvent. Then we have mole fraction, which we represent with chi. This is read as chi. It is about number of moles of solute upon total number of moles of solution. So that implies this is equal to number of moles of solute by solute plus solvent. These are the terminologies that we will be using. Is it clear? Next is about percentage compositions. Percentage compositions. Percentage composition include percentage weight by weight, which is weight of solute upon weight of solution multiplied by 100. Okay. Similar logic we'll be adding for percentage weight by volume. So here it is weight of solute upon volume of solution. And likewise, we'll be adding volume by weight, which is volume of solute on weight of solution. And finally, percentage volume by volume, which is volume of solute upon volume of solution into 100. Okay, beta. These are the percentage compositions. Other than that, we have parts per million, parts per million, which is ppm. This is also a representation of concentration or strength. Okay, so ppm includes weight of solute upon weight of solution into 10 raised to power of 6. Typically, if this is taken in weight, this should also be taken in weight, so that the value what you are getting should be in ppm units, like this. Okay, this is about parts per million compositions. So these are the concentration terms that we must know. Okay, beta. Lastly, the last one which we left is about normality n. Okay, now if you notice the difference here, we use the terminology molarity, molality, mole fraction. All of them has one thing common, which is number of moles of solute. Okay, while normality have only that thing uncommon, it is about number of equivalents of solute upon upon volume of solution in liters. Okay, that implies capital N is equal to number of equivalents. So EQ divided by volume in liters. Okay. So this has very close relation with molarity if you have seen it. So I can use the terminology like this: relation between molarity, and normality. So you can see molarity into volume is equal to number of moles of solute, while normality into volume is equal to number of equivalents of solute, EQ of solute. Correct? So here, if you relate this, volume is one thing we can relate. So number of moles of solute by molarity is equal to equivalents of solute by normality. Correct? Or I can say normality into number of moles of solute is equal to molarity into equivalents of solute. Got it? This is another relation between molarity and normality that we must know. Clear it up? Now, how do we define these equivalents? That is more important for us. Okay, let us understand and define the equivalents. Equivalence. Right? Equivalence is a term which is very similar to number of moles. How we write number of moles, it is the same way we will write down. Okay, which means it is about weight of the substance, weight of the substance with respect to equivalent weight of the substance, equivalent weight of the substance. If you see the analog with respect to the number of moles, so the number of moles of solute is equal to weight of solute upon molecular weight of solute. On a similar lines, equivalence of a solute is equal to weight of solute upon equivalent weight of solute. So that's one close relation between number of moles. So you can see number of moles of solute into molecular weight is equal to equivalent weight of solute into equivalent weight, right? So this is another important relation we will get, how to relate number of moles and equivalents. Got it? Now we are slowly getting into the logic. What exactly is equivalent weight? So you can see, let us define equivalent weight, EW. Got it? Equivalent weight. So basically, equivalent weight is the terminology we use when we are trying to express the molar mass with respect to a certain factor. So that is, equivalent weight is always equal to molecular weight upon a factor. Got it? Now this factor has many names. The factor that we use is called as N factor or Z factor or valency. You can call it as valency or also known as valency factor. So you can see so many different terminologies are used to express that factor. Okay. Now these terms, we use it in different, we use it based on a different substance and their nature. Got it? For example, if I use the word factor here, I need to first distinguish the subjects we are studying, substances which we are studying. See, the substance which we study, the substance which we study can be mainly categorized into three parts. Okay, either acids, bases, or salts. Got it? Of course, we have water also, which is not completely acid, base, or salted. Okay. So we use the word acid when we express that it has uh, ability ability to release H plus ions, and H plus is nothing but proton, correct? H plus or proton ions here. Clear? Ability to release H plus ions. Base is about ability to release OH minus ions or accept H plus ions. Then we say it is base. Salt. Salt, you know, it is only about combination of an acid base part, correct, where H plus and OH minus is lost. So salt is combination of acid and base after removal of H plus and OH minus. Got it? Water is like a universal solvent, can be treated as acid or base. Such kind of a solvent is called amphoteric substance. Clear? Is this logic understood, beta?
Yes, sir.
Right. Now, equivalent weight, to calculate the equivalent weight of a substance, first we need to understand its factor. For any substance, factor. The factor would be different for different substance here, whether it is acid, base, salt, or water, it will be different. So let's see. Valency factors for various substances. Check out. Valency factors for various substances. Got it? The first factor, the first one is for acids. For acids, number of ionizable, number of ionizable H plus ions, H plus ions is valency factor or N factor. Got it? In case of bases, it is number of OH minus, sorry, ionizable OH minus.
Sir,
Yeah, beta.
so, what is the difference between ionizable OH minus and normal OH
I'll show you
minus?
with examples. Okay. Is the valency factor. Is the valency factor. Now, let me show you how it is. For example, if you notice these two examples, suppose I have HCl, HBr, HI, HF, correct? These four acids, if you notice, correct, their valency factor or N factor, if you compare, it is 1. Why? Because if they ionize into any aqueous solution, it will convert into Cl minus, Br minus, I minus, and F minus. Doesn't matter whether it is a strong acid or a weak acid, we just need to check how much is its ability. The ability is it can release one H plus out of it. Okay. Likewise, if you have H2SO4, H3PO4, okay, HClO4, HNO3, or H2C2O4. For all of these cases, if you notice the valency factor, it can release two H plus ions, making it SO4 2 minus, PO4 3 minus, ClO4 minus, NO3 minus, C2O4 2 minus. Correct? So, which means in all of these cases, if you compare the valency factor in this case, you will notice this is 2, 3, 1, 1, 2. Correct? These are the valency factors. Now, let me show you some cases. For example, if you take CH3COOH, okay. Now, for this case, if it loses H plus, what does it become? It will become CH3CO minus. Next, I have H3PO3. If this loses, it will become HPO2 2 minus. If you have H3PO2, it can become H2PO2 minus. Now, if I ask you what is the valency factor in this case, answer is 1. Valency factor in this case, answer is 2. Valency factor in this case, answer
One.
is 1. Why is that so? Check out the buildup of the structure. CH3, C double bond OOH. This is the structure of acetic acid. Okay. While if you notice P double bond O, O and H, O and H, and this is directly connected to H. This is about H3PO3. This is about CH3COOH. And likewise, P double bond O, OH, H and H. Okay, this is about H3PO2. Got it? So from here, if you notice that this hydrogen is the one which is ionizable. These three are not ionizable. Is that clear? That means although there are hydrogens, but are they able to get ionized? Not,
No.
not necessary. Okay. Likewise, in the second case, you will see this hydrogen and this hydrogen are ionizable. This one is not ionizable. Similarly, here we can see here we can see only one hydrogen is ionizable. These two are not ionizable. Okay. Now, let me go back here to the definition. Whenever you have an ionization being defined, correct? That is how many number of ionizable hydrogens which you are giving. That is also called as basicity of acids. Likewise, the number of ionizable OH minus are called acidity of bases. That is how much acidity it can handle. Base can handle how much acidity, or an acid how much it can handle basicity. That means how much base it can handle. That defines basicity, and here it defines acidity. Is that clear?
Yes, sir.
Right. So from here, based on these structures, you can clearly make out that their basicity in this case, if I ask you the basicity of this cases here, it is clear that the basicity in this is 1, here it is 2, here it is 1.
One.
Okay, this is what I meant by basicity. Likewise, suppose if at all I have AlOH thrice, NaOH, BaOH thrice. Okay, if you compare the if you check out its ability to release OH minus, what does it become? Al plus 3 plus 3 OH minus. It will become Na plus OH minus. Barium 2 plus 3, sorry, 2 here. So 2 OH minus. So this time I use the word acidity. So acidity in this case is 3, here it is 1, here it is 2. Correct? So this is the basicity or acidity, whatever we are studying. Correct? So valency factor of acid or base is its basicity or its acidity. Clear it up?
Yes, sir.
So if I have to calculate the equivalent weight of H3 PO4, then what will I write? It is molecular weight upon 3, which is 98 by 3. Got it? Likewise, if I have to calculate equivalent weight of H2SO4, I'll be writing this as molecular weight of H2SO4 by 2. If I have to calculate equivalent weight of aluminum hydroxide, then it is molecular weight by 3. If I have to calculate equivalent weight of HCl, it is simply molecular weight by 1. Equivalent weight of, bismuth hydroxide, BiOH thrice, that will be molecular weight by 3. Equivalent weight of, NaOH will be molecular weight by 1. Right. All this part is clear, beta. How do
Yes,
we
sir.
figure out equivalent weight? Any doubt?
No, sir.
Right. So equivalent weight is subject to the nature of the substance. So if it is for acid, its name is different. It's for base, it's different. Now let's see for salt. In case of salt, in case of salts, equivalent weight is the total positive or negative charge of the species. Got it? For example, if at all I have barium phosphate, Ba3, PO4 twice, then The equivalent weight will be equal to molecular weight of barium phosphate, that divided by total charge. How much is the total charge now? Check out. Basically, if this splits, the total positive will be 3 times of barium 2 plus, and this will be 2 times of phosphate 3 minus. So the charge, if you notice, 3 into 2, 2 into 3. So total how much we have? 6.
Six.
Okay. So this 6 becomes the valency factor. I suppose that is clear.
Yes, sir.
And notice, in case if you have Na2CO3, sodium carbonate, then equivalent weight will be equal to molecular weight by 3. Sorry, molecular weight by 2. Okay, total positive charge or total negative charge. What if I have like this? See, I have K2SO4 dot Al2SO4 thrice dot 24H2O. This is called potash alum. This is a potash alum. Now the equivalent weight will be equal to total molecular weight defined by the valency factor. Now check out valency factor. Valency factor will be equal to the total positive charge. Total positive charge is 2 in the first case, and every aluminum will have 3. So 6 plus second case. Correct. And this is the total positive charge if you notice. So the total positive charge is 8.
Okay.
Likewise, you can check out the negative charge also. So 3 goes minus 2. So minus 6. And SO4, here it is minus 2. So minus 6 minus root 2 divide, multiply that, you will get this as 8. Okay. So that becomes the valency factor. So equivalent weight in this case will be molecular weight by 8. Water has no role to play here. So whenever it comes to salts, you need to check out like this. Okay, beta.
Yes, sir. Sir,
This is about the hmm?
what does the dot mean?
Okay. Basically, here the dot means this much water is accumulated when you try to isolate them as a crystal. Got it? This entire thing is one molecule of crystal. Got it? Basically, it is like this, Devarshi. You take K2SO4, a white color powder. Got it? Then you take aluminum sulfate, another white color powder. Add very little droplets of water into it. So they will have cohesive forces along them. They'll start coming together and try to convert into crystal form, and becomes very hard. That crystal will become very hard. Okay. Now, if you break that crystal into one molecule, in that one molecule, this is the composition you will find. Got it? Clear now? These type of compositions where you have one such molecule combined with dots is called as double salt. These are called double salts. Okay. Double salt means it is combination of salts. Okay. Clear? Right. Shall we go ahead? Hmm. Now notice the next one. We got an idea about how the equivalent weight works here, but equivalent weight can subject to variation depending upon the chemical reactions also, right? So check out equivalent weight and valency factor in chemical reactions. Chemical reactions. See, for instance, if I take H3PO4 and treat that with 2 moles of NaOH, and it is giving a product Na 2HPO4 plus H2O. This is how we have written it. Okay. In that case, what would be the equivalent weight in this case? For that, we need to require what is valency factor. So let me write down valency factor here. Have you noticed that it usually has ability to donate three hydrogens, correct? Because all three are ionizable. But in this reaction, is it giving all three? Check out these H3PO4 has given two of them and converted into this part. Since it has only given two of them, we will write it as 2. Here in NaOH, every one molecule of NaOH is consuming one H plus, and that means it is giving away one OH minus. So it is 1 only. Okay. And this is a salt kind of a form now, right? This is a salt form. So what is the charge on it? Total positive charge is +2. And HPO4 is -2. So total based on total charge, the valency factor is 2. Water can always be regarded as either acid or a base. As an acid, it can give 1 H plus. As a base, it can give 1 H plus. So it is always going to be 1. Okay, these are valency factors. Based on that, what will be equivalent weights? So that is equal to molecular weight by 2. It is molecular weight by 1, molecular weight by 2, molecular weight by 1. Done?
Yes, sir.
Clear?
Yes, sir.
So it might be varying. That means the same equivalent weight earlier we wrote it as molecular weight by 3. See, if the equation is not given, you will always take up the maximum value. Got it? If the equation is given, you will go as per the chemical equation. Right? Now, how do we figure out the valency factor of ions if only ions are given? Correct? Right? In the case of ions, you only check out the total charge carried by the ions. Total charge carried by the ions is their valency factor. For example, sulfate SO4 2 minus, SO3 2 minus, S2 minus. Got it? While if you take hydrogen phosphate HPO4 2 minus, okay, HPO3 2 minus, CO3 2 minus, C2O4 2 minus, CrO4 2 minus, MnO4 2 minus. Got it? If you have these kind of terminologies here, so we can always have anything of this kind. Phosphate is done. Yeah, all of them are done here. So if you notice all of these, for these cases, for all the above cases, for all of these cases, valency factor is 2. Okay, beta, the valency factor in this case is 2. Likewise, if you have PO4 3 minus, correct? If you have PO4 3 minus, then uh, Fe CN6 4 minus. Got it? NH4 plus H3O plus RCOO minus. Correct? RCO minus. And N3 minus. Okay? NH2 minus. OH minus. Correct? Cl minus. ClO3 minus. ClO4 minus, correct? S2O3 2 minus, S4O6 2 minus, okay? NO2 minus, NO3 minus. So in all of these cases, if at all I have to figure out what is the valency factor, just check out the charge and that should be the case.
1, 1,
1. Here,
3,
3.
1,
1,
1,
1,
1,
1, 1,
1,
1,
2,
2,
2,
1,
1.
and 1. All good?
Yes.
These are very frequent ions which we will come across. So if these ions are come, you should be able to figure out what is their valency factor as well. Got it? In fact, in case if at all I give you a salt form, correct? The best way to judge here is how they are connected to group 1 and group 2 elements. Got it? Let me tell you. In periodic table, group 1 elements means lithium, sodium, potassium, rubidium, cesium. All have +1 charge in combined form. Combined form in salts. Similarly, when it comes to group 2, suppose in periodic table, if you're talking about group 2 elements, that includes beryllium, magnesium, calcium, strontium, barium, in fact radium also, but radium is radioactive, so I'm not taking that into picture. So that have +2 charge in combined form in states. So you always notice this one, that what is the charge they carry, then you separate them out. After you separating it out, you will get an anion and decide what is the charge on it. For example, I have been given KXPO4Y. Find XY. They are clear? You have to find XY. Likewise, if you have, you know, K2MnO4Y, got it? I have Ca3, correct? Ca3 and phosphate Z. Find Z here. Okay. Similarly, if you have Zn and Zn P times NO3 twice, correct? So calculate what is the value of X. So our objective is to find out X, Y, here Z, here P, like that. You need to check out what is the value they can have, so that we are clear what is the kind of salt we are talking about. Hmm? Similarly, if at all I have NaP and C2O4Q. So again find what is P and Q. Got it? So check out what are the names you can get here. What are the values we can get here? In the first case, X is how much? 3 and Y is 1. Because phosphate overall will be -3, potassium is overall +1. Cross multiply that. Here, potassium overall is +2. So MnO4 minus has to be -2. So Y has to be how much? 1. Clear? Here, phosphate has to be, if calcium is 3, phosphate has to be 2. Here it has to be 1. And here P has to be 2, Q has to be 1. So I hope you understood how to judge on the salt forms. Yeah,
Yes, sir.
right. Sorry. Next, notice this one. We got to know how the equivalent weight works in all the cases. Okay. Now we need to figure out what exactly is the importance of these equivalents. Okay. Why is that so important to learn about this valency factor, equivalent weights, right? How is it going to help it? To understand this, we need to learn what is known as law of equivalence. Law of equivalence. Got it? According to the law of equivalence, in a chemical reaction, in a chemical reaction, okay, all the reactants participating in reaction, participating in reaction, and all the products formed will have same number of equivalents. Okay, same number of equivalents. So the number of equivalents will not be different. Their moles may be different, but number of equivalents will not be different. Got it? This is what he meant. Now, this is what we call it as law of chemical equivalence. Let me show you with an example. Suppose if you have 2 moles of NaOH plus H2SO4, our expectation is it will become Na2SO4 plus H2O. Na2SO4 plus H2O. What is a valency factor in all of these cases? Please check. NaOH valency factor is 1. H2SO4 valency factor is 2. Na2SO4 valency factor is 2
Two.
because you can see total positive charge. This is salt.
Two.
Since it is salt, total positive charge. And here valency factor is 1. Hmm? Got it. So if you balance it, basically you'll get 2 here. This is what you'll have. Okay. But the valency factor is 1. Now, if you know the valency factor, what are the number of moles here? Check out number of moles as per the stoichiometric ratio here is 2 moles is to 1 mole is to 1 mole is to 2 mole. Correct? Now, let me come to the factor here. If you go back to this equation here, correct? Where is it? Yeah, when we define the equivalent weight here, let me bring this back. Correct. So while we were learning, I told you that number of moles can be represented in terms of equivalence. Okay. Now check this out. I'm just modifying this part. Number of moles of solute is equal to uh, into molecular weight is equal to equivalence of the solute into molecular weight upon the valency factor, because EW is molecular weight upon valency factor. Correct? So from there, you can clearly see that molecular weight here and molecular weight term here will get cancelled. So that includes the number of equivalents of a solute is always equal to number of moles of solute into valency factor.
Hmm.
Is this point clear?
Yes, sir.
Now come back to this here. So what can I write in terms of number of equivalents? Number of equivalents is equal to number of moles into valency factor.
Yes.
Number of moles is 2 into valency factor. 1 into valency factor, 1 into valency factor, and 2 into valency factor. So what did we notice?
Oh, it's same.
Same number of equivalents, correct? So they all possess same number of equivalents. same number of equivalents. And that's what we call it as the law of equivalence. So many a times this will help us a lot. That is, in reactions where, you know, idea of chemical reaction is not given. We don't know how much is the reactants and everything. But what are the moles, how it is balanced, this is all not known. But one thing is for sure, even if I take one equivalent, sorry, even if I take the equivalents known for one reactant, that is sufficient enough to figure out what is the equivalence of the product as well, correct? So that is a logic, we can use it always. Clear? That's how it is going to be helping. Okay, beta?
Yes, sir.
Now, when it comes to chemical reactions, they themselves we can categorize into two forms, beta. One is non-redox reactions. Non-redox reactions. The other one is redox reactions. Redox reactions. Correct? Now let me first emphasize on non-redox. Now, in the case of non-redox reactions, we can say the first part is in the case of non-redox, we can say acid-base reaction is one such kind. Acid-base reaction. Clear? Displacement reaction. Next, double displacement reaction. Got it? These type of reactions are simply precipitation reactions and everything. These are all non-redox reactions. Correct?
Yes,
For
sir.
non-redox reactions, valency factor is determined based on nature of substance. It is based on nature of substance. Okay. Therefore, if you have something like AgNO3 plus KCl, the reaction is 100% done. It will give you
APGL.
AgCl as a white PPT plus KNO3.
KL3.
Okay, so this is the reaction that you will notice. So figure out valency factor in all the cases, beta. First case, 1,
1.
1,
1.
1, and 1. Correct. So these are the valency factors. Likewise, in case if you have a reaction like NaCl, right, reacting with Ag2CO3, so we can get 2
AG.
moles here, Na2CO3 plus 2 moles of AgCl. Any doubt?
No, sir.
Right. Here also, if you notice the valency factor, here it is 1, here it is 2, here it is 2, here it is 1. And any acid-base reaction for that matter, if you have H2SO4 plus, you know, calcium hydroxide, it will convert into calcium sulfate
Plus.
plus 2 moles of H2O. Acid-base reaction. So valency factor in this case is 2, 1, sorry, 2, 2, 2, 2, 2, and 1. Is that okay?
Yes, sir.
This is how we can find out the valency factors in all the acid base reactions or displacement reactions or double displacement reactions. Correct? See,
Yes.
how do we read in these reactions, beta? We can say the number of equivalents of H2SO4 is equal to equivalents of calcium hydroxide is equal to equivalents of calcium sulfate is an equivalence to uh, equivalents of H2O, equivalence of H2O. Done. So whatever we discussed, this is all about non-redox reactions.
Mhm.
In all the non-redox reactions, acid-base reaction, displacement, double displacement reactions, you just check out this way and equate it. Okay.
Yes. So
Next is about redox reactions. Now let me introduce what is redox reactions.
the
Sorry, one second.